Let's try a few problems now involving the conservation of linear momentum. In this example, we have a larger car. This one is 1,800 kilograms. And this one begins at rest, sitting at a stoplight, while a smaller car comes up behind it and rear ends it. The smaller car is going to be 900 kilograms. And you can see from the problem that it's moving at 20 meters per second. Now, we can read in the problem and realize that these two cars after the collision are going to become entangled. Basically, what we're saying is that they're going to be one big mangled mess and one lump mass. Now, what we are looking for is the speed of these entangled cars, or the speed of this wreckage after the collision has occurred. Now, what we're looking at here is the idea that momentum can be conserved in collisions. As long as there are not any outside net forces acting on the system, which over the small instance of just before the collision and just after the collision, any outside forces can be fairly negligible. So we will assume that our momentum is going to be conserved. What that means is we're going to look at the initial momentum coming into the problem. So before the wreck actually occurs, we have the smaller car moving at 20 meters per second. So its momentum would be its mass times its velocity. We have the larger car, which was sitting at rest, so its mass times its velocity. Now, after the collision occurs, these two cars are going to stick together. So basically, the total final mass is going to be the combined mass of both cars, with both of them moving at some final velocity that is going to be the same because they're both stuck together now in this collision. If you'd like to take a moment to pause the video and solve for V sub f, go ahead and do that now. What you'd find is that when you solve for the final velocity of this wreckage, you get about 6.67 meters per second. Check and make sure that you get the same thing. This particular example was one that would be categorized as an inelastic collision. Remember, inelastic collisions are ones where the kinetic energy cannot be conserved and will not be conserved. That means that these objects are going to lose some of that initial kinetic energy to things like deformations in the car, sound that's going to occur, heat that's going to be generated, those types of things. And even though kinetic energy cannot be conserved in an inelastic collision, momentum certainly can be. Especially when things stick together, when two things end up being stuck together as one, that is actually called a perfectly inelastic collision. Now let's look at the next slide and try a collision that would be considered an elastic collision. In this example, we have a block of mass 1.6 kilograms. It's going to be moving to the right with a speed of 4 meters per second. So here's my block, 1.6 kilograms. It's moving at 4 meters per second. Now this block is going to collide with a larger block. The other block is stuck to a spring. So here's the spring that's kind of stuck between the two of these guys. The second mass is 2.1 kilograms. So this one is larger. And it starts off by moving to the left at 2.5 meters per second. Now, because momentum is a vector and velocity is a vector, I'm going to call this one negative 2.5 meters per second. Anytime you're working on momentum problems, make sure that you are keeping track of direction. Choose a direction at the beginning of the problem. I chose to call right the positive direction. You can make your choice however you want, but you do have to stick with whatever direction you choose for the duration of that problem. Now we know that this spring has a spring constant of 600 newtons per meter, and we're going to look at what happens when these two blocks collide and stick together through that spring. Now, because a spring is something that will exert a conservative force, this would be categorized as an elastic collision. And we're looking at the point in time when these blocks are beginning to sort of come together with the spring in between them, and that smaller block has slowed down to 3 meters per second. Again, we can use conservation of linear momentum to set up this problem. We begin by looking at all of the momentum at the beginning of the problem and set it equal to the momentum at the end of the problem. In the beginning, we have the 1.6 kilogram block moving at 4 meters per second. And we also have the 2.1 kilogram block. It's moving at negative 2.5 meters per second. There's all of our initial momentum. Now if we were to look at the momentum after, or once the two blocks are coming together with that spring, we have the 1.6 kilogram block now moving at 3 meters per second. And the question is, how fast is the 2.1 kilogram block moving? If you would like to take a minute to pause the video, go ahead and do that. You can solve for your V sub f. When you find that value, you would get about negative 1.74 meters per second. It makes sense to have a negative value because the larger block is still moving to the left, so it still has a negative value, but it's slowing down as it's moving to the left, just like the 1.6 kilogram block is also slowing down. As I erase this, we are going to try a few other examples, and we're going to look at some other questions. Another question that's asked here is, what distance is the spring compressed? So if you remember what we have going on here, we have the smaller and the larger blocks now compressing the spring that's in between them. Now, because this is a conservative force that's being exerted by the spring, and because we are on a frictionless surface, this is now an elastic collision, and elastic collisions will conserve energy. What that means is that all of the energy that we start out with in this problem has to be equal to the energy that we have in the end. Now, in the beginning of this problem, we have each of these objects moving towards each other. That means that we could find a 1/2 mv squared of each of the objects as our initial energy. So we have 1/2 the mass of the smaller block and its velocity squared, plus 1/2 the mass of the larger block, multiplied by its velocity squared. Now again, we still have that negative 2.5, but because we're squaring that, your negative sign is going to go away, and that negative won't make a difference here when we talk about energies. This is all the initial energy. Now, after the collision has occurred and these two blocks are compressing the spring in between them, each of the blocks were still moving. We still have the 1.6 kilogram block moving. It's now moving at 3 meters per second. We still have the larger block moving, and its velocity, which we just found, was 1.74 meters per second. But there's one other term that belongs on this other side of the equation. For the final energies, it's not just the kinetic energy of each block moving, but where else has energy gone? In this case, energy has gone into the compression of the spring. So on this right-hand side of the equation, we actually need to tack on a third energy term. It should be a 1/2 kx squared. The k of the spring is 600, and the compression distance of the spring is actually the variable that we're looking for. So in this case, we could set up a conservation of energy equation to go along with this problem as well, because this type of collision is elastic. So we have all of our initial in the beginning of all of our energy at the beginning of the problem. We have all of our energy at the end of the problem, and these two things now need to be equal to each other. If you'd like to pause the video and try it for yourself, see if you can solve for the x value. Actually, let's just get the x all by itself. So if you solve for x, you'd find that this x value comes out to be about 0.173 meters. Check yourself and see if you got it.